So I hope from this topic of accurate relative atomic masses or mass spectrometry, you already have the idea that we wait a second that we use it for the purpose of getting the accurate relative atomic mass from the relative isotopic masses. So I'm not going to go into the structures and stuff. That's not the question. Let's discuss about these. The very first mass over charge ratio and relative abundance proportions. This is an example of lead and its different uh, isotopes. Now, as soon as you see a graph, this graph can tell you a lot of things. First of all, isotope. It tells you about the number of isotopes, right? You can see one, two, three, four. So you got four isotopes. And then it gives you isotopic masses, which is pretty easy. Whichever one they land on, this landed on 2000, 204, 206, 207, 208. So you have those isotopic masses. Then it gives you the relative abundances, how high. It will give you a very good idea of the relative abundances. Just to be on the safe side, adding up these abundances and finding out the total is a very good idea of judging whether these are the only isotopes that lead up to a total of 100% or would there be another? Because this might be a trick in there in the question. Also, this is going to further help you with the relative atomic mass, or I shouldn't be writing this short form AR. Now, in case of AR, you have the formula that you take the mass of the isotope and you multiply it with your relative abundance, right? Of you do that with the first isotope, then you add it to the second one, then you add it to the third one. If this total comes out to be 100, you divide it by 100. If this total comes out to be 99, you divide it by 99. That's the purpose of doing this. Okay, because the
All
number over
right.
here and a number over here will make sure that you get an exact answer over here, right? So this, since this is done for 100%, the total 100% is calculated over here. This gives you the idea. Okay. This also tells us the same thing, but that I just told you, dividing figures, multiplying, which gives you the idea. We do it for neon. This example works great. Year of neon is calculated because there is 20, this is 90.9%, there is 21, 0.43%, this is 22, 8.8%, divide them by 100, 20.2. At least the three significant figure rule is good. Going any higher with four or five gives you more accuracy in time. Going higher than four does not make sense. It would be a wastage of time. At least three, a maximum of four works great. All right. So for oxygen, they have given the precision, the high level of precisions actually help us with distinguishing between different substances, right? The example of oxygen has been taken. Why? Because oxygen and sulfur actually helps us with this. With SO2 or S2 would give us the idea. Since oxygen is 16 and sulfur is 32, if we go with these whole numbers, we're going to end up with the same value. But if we don't go with these whole numbers, instead we go with these accurate numbering, we might be able to differentiate between these two because the answer won't be the same. Go ahead and add these values up, and you'll understand the answer to SO2 for the calculation of MR or the calculation of MR for S2 would be entirely different. And that's how this high level of precision helps us with understanding what that is. Make sure you keep the same level of precision, which is actually taken as help from the values given in the question. Otherwise, remember your periodic table discusses up to one decimal point values. For example, magnesium is not 24. Magnesium is 24 in the IGCSE periodic table, but magnesium is exactly 24.3 in A-level periodic table, which gives us the higher level of precision edge. So that's why always take help from the periodic table and do not miss out on those values. Now, let's come to the identification of organic compound using mass spectroscopy. This material that has been added to AS recently for 2023 papers, and which actually makes the whole thing difficult for the student. Now, the main use of this is to make sure that the identification of organic compounds can be held against the fingerprinting technique. Remember, the fingerprinting technique is this, that we match the spectra of known substances in the database, and we have a really big database with us on the internet or in the books, so that can really help us. Remember, the high energy electron knocks out electrons from the molecules and breaks covalent compounds, covalent bonds. And for example, propanone is taken, and you have these three values. Of course, this might be this, we don't break any bonds. But if we do break bonds, what is this and what is this? One might think. Now, take a look at the structure. It works like this, right? Now, these two ends are the same. If you break one of them off, what is this up to? And what is the rest of this up to? Breaking them off like this on just understanding basis for just hit and trials will make you great in finding out this and this. This might be equal to 15, this might be equal to 43. You never know. So as soon as you look at the compound, going for a hit and trial method can actually really work for students as starters. What I just did is that I broke a carbon-carbon single bond and broke the entire structure into two pieces. Who knows? It might be those two pieces. Maybe you get one of them and you might need to break another bond to get another piece out of it. So it really depends upon the substances and the work you can do with it. Now, they have compared it with mass spectrum of germanium. Remember, this is different from the previous one. These are isotopes, different possible isotopes. This is fragmentation, breakdown of covalent compounds, organic compounds in this specific case. So what do they break down into? Here we go and explain molecular ions. And at the same time, we give you an idea how the high energy electron are going to break up a bond, will produce a free radical for us, take away an electron out of it, hence leaving a molecular, cationic molecular ion, to be exact, positive molecular ion, hence N plus, right? Though this is not exactly telling us this is the molecular ion we're talking about this, but molecular ion usually they talk about the base peak. The base peak is the peak of this one, the biggest number. However, these are known as fragmented parts. And these fragmented parts, actually this one caused the peak at 15, this one caused the peak at 40. That's what I was talking about. I hope that clarifies it, does it? I'm doing a little
Yeah, it
fast,
does.
but that I'm doing just for the sake of paper. We do not need to fall into the nitty-gritties at this point. Okay,
Yeah, yeah.
so moving on. Now, remember that fragmentation breaks down compound. There are certain bonds that break. M over E 15 usually represents this. 43 can be this or this. Now, which are the bonds that usually break? Remember, this one would usually break, this one would usually break, this one would usually break. Since your book points these out, these are the most common ones you're going to go for. So try breaking these first, finding out your fragmented portions, relating them to the given values. And if these don't work, go ahead and break other bonds, whichever ones you like, just to get to the value. Okay. The few examples are given over here, most common ones, 15, 28, 29, 43. But there can be questions out of these examples. And past papers are going to prove that. You can go for a substance, actinic acid. You can literally work your way. Now remember, the base peak or the highest peak actually on your right is usually of the whole compound. So work your way. It's CH3, COOH. How much is the MR of CH3, COOH? That's probably already 16. So you need to work fragmentation for these three. That's how it goes in every question, almost in every question. Okay, coming to the next part, high resolution mass spectra, which actually gives the question a little bit of lengthy parts and makes the whole question look more difficult to you. High resolution mass spectra actually give us values to more decimal points so that it's easier for us to calculate and find out the accurately possible answers. And this also explains why we take carbon 12 as the standard. When you see that the zero is coming in front of it as compared to the other elements, now this definitely makes sense that why we took carbon 12 as a standard for calculating relative atomic masses for different atoms or elements in the periodic table. The accuracy should make a lot of sense apart from other factors. But moving on, now, there is a very good example that discusses why we exactly go with high resolution mass spectra. Take this example or this example, you'd see that both of them end up at the MR of 45. How would we know which one is this? But if we go with high resolution mass spectra, notice the values have a difference. As soon as we deep, deep, deeper, dive deeper into higher decimal values, first decimal, second decimal, third decimal values, you get your difference. But we go even higher than that, just to make sure that we are doing it accurately, as much accurately as we want to. Now, when we delve deeper into high resolution spectra, there are other things that we need to understand. As soon as we go with high resolution spectra, there is an M plus one peak that we usually see. And this M plus one peak is really very small most of the time. For example, we're talking about ethanol. See, this is ethanol, but this M plus one peak. Why are we really getting that peak? Carbon 13 isotope. Now, you probably already know carbon exists in 13, 14, and 12. 12 exists as 98.9%. This exists as 1.1%, and this exists in traces, which means in such a small amount, we do not usually quote percentages for this. This is also radioactive. So let's not consider this. For these two, this would usually end up to 100% in total. If you go with higher exact values, this would be 98.88 something. Now, this 1.1% really matters, and that's why this peak is this small. And this 1.1% value is then used to calculate the number of carbon atoms in an organic compound, the most common question you're going to see in past papers. We use this formula to calculate the number of carbon atoms in a compound. So out of the 100 total, 1.1 is the carbon 13 percentage. So this is the M plus peak, the one for the whole compound, and this is M plus 1 peak, when one out of those carbon atoms is made of carbon 13 isotope, hence this 1.1. So if we have the abundances to these peaks, just two values, we can literally calculate the number of carbon atoms in the organic compound. This is how easy it is. Let's take a worked example at this. And it is going to be the same in question papers, and it's literally that easy. You get a relative abundance of M plus peak, you really get a relative abundance which is much smaller for an M plus 1 peak. Put the values over here, get your answer. Move your answer to the closest whole number value, and this is the number of carbon atoms in each molecule. You might need to move it to your closest whole number value. It can be 6.1. 6.1 means 6. All right? There are questions confusing like this.
All right.
Don't worry. Just go ahead and go with the whole number value and you'll get your answer. This is how easy it is. The next question also shows you the same thing. 62 to 4.1, you get it. Okay. So how many carbon atoms are there in the hydrocarbon? You get to know. Since he's already told you 84, you can work with the structure. If he tells you it's 84, the value is 84. When you calculate this formula, you get your answer. Let's suppose it is made up of just C's and H's, and there are 6 carbon atoms. Let's suppose you work this one out and you get an answer of 6 carbon atoms. You can work the number of hydrogen atoms with it. This is the easiest thing that you can do with this value, with this MOV value. All right. Now, this may not be told as a part of the question and may be a part of the graph. Be clever, take it out of the graph because there are numbers on the graph right there and then. And if C6 is equal to 72, this probably is 12. That's how the total is 84. This is C6 is 12. We're talking about hexane. There you go. You probably already have the identity to it. Sorry, hexene. My bad. Hexene. Hexene or cyclohexane.
Hexene. All right.
Because CnH2n is either alkenes or cycloalkanes. We have studied that. So if you have a good knowledge of organic chemistry, you can be really good at this, right? Moving on. M plus
Yes, sir.
2 and M plus 4 peaks. Remember, M plus 2 and M plus 4 peaks has everything to do with these two, right? It's an extension content. It's not a part of the syllabus. So we teach this to students. We don't really know whether the questions with this would come or not, but it definitely would be a part of A2. So we make sure we teach this at this point. Okay. So moving on with this, let's clarify it because they might use this and ask the question with the previous part. So if you're good with this, you won't have a problem with it. Now, if you look at chlorine, these are the two isotopes, and that's their percentage value, 3:1. These are the two for bromine, 1:1. So as well as the M plus 1 peak was there, and remember, carbon was 12 and carbon was 13, so there was an M peak and M plus 1 peak because the difference between 12 and 13 is 1. For chlorine,
All
that's
right.
actually 35 and 37. So obviously we'll get the M peak over here. And if there is any 37 involved, we'll get an M plus 2 peak. Same goes for bromine. Bromine is either 79 or bromine is either 81. So we'll get an M peak with this and we'll get an M plus 2 peak with this, which clarifies the rate M plus 2 peak, right? I'm going to clarify M plus 4 peak a little later. Let's first clarify M plus 2 peak. So if you have one carbon or one bromine atom per molecule, you're going to get an M peak and you're going to get an M plus 2 peak. M peak represents your original chlorine or your original bromine, and M plus 2 peak is going to consider your second isotope of chlorine or maybe the second isotope of your bromine, right? Which is clarified over here. Now, these peaks would have this percentage difference to them. The peak would literally be 3:1. This should be double, this should be triple, 3:1. The peak size would be the size, this percentage applied to it, because there are supposed to be 75% of these isotopes and 25% of these. So 3 times the peak would be the size of Cl35 and 1 times would be the size of Cl37. So those molecules which are made up of 35 would constitute this peak and those made up of 37 would constitute this peak. So that would be the literal difference between the peak. This must be the M value and this must be the M plus 2 value. Let's suppose we're talking about CH3Cl. What's the MR to this one? If it's 35, the MR must be 35 plus
Mm-hmm.
15. So this would be 50 and this would be 52. Makes sense? I recently calculated this to
Yes,
be
sir.
15. So I hope this makes sense. 15 plus 35, 15, 52. If that's 35,
Got
it's
it.
52. If that's 37, that's if that's 35, it's 50. If that's 37, it's 52. All right. So now you
Yes, sir.
understand what the M plus P 2 peak is going to show you. This is just for chlorine. For bromine, the entire thing changes. Of course, bromine would have a higher mass, 79 and 81. Okay. An example of chlorobenzene would be shown next. So this is how easy with one chlorine or one bromine atom is. With two chlorine and two bromine atom, the chances become a little bit different. Let's consider two chlorine atoms first. Now the chances, if you have CH2Cl2, I'm taking the exact example that is shown over here, you have two chlorine atoms. Both of them can be made up of 35. First one 35, second 37, or second 35, first 37. This can be the chance, or both can be made up of 37, right?
Yeah.
Now this would form M peak because both of them are 35. This would form M plus 2 peak because one of them is 37, so does this one. But this one would form M plus 4 peak. Why? Two steps in this and two steps in this.
All right.
Now, chlorine, ratio chlorine, my bad, 35, 37 was 3:1, 75 and 25. We need to work these one out, this, and this, for M plus 2, and for M plus 4. I hope you understand the double ratio system in math. It works like this, 3:1, 3:1. This is multiplied by this, so the answer is 9. This is multiplied by this is multiplied by this. So 3 plus 3, this would be total to 6. And then this is multiplied by this, so there's 1. Right? You
Yeah.
understand this double ratio system in math? I hope you're a
Yes.
math
Yes.
student, so this shouldn't be a problem. This usually comes as a problem to the biology students. We need to explain them how this works. Okay, but I don't think I need to explain this to you. So this clarifies the
Yeah. It's fine.
percentage. So literally, the M peak would be 9 times higher, the M plus 2 peak would be 6 times higher, and the M plus 1 peak would be 1 time higher. M plus 2, M plus 4. It would be literally this high. This is the height of the peak. And as soon as we see peaks like this, we can really identify that the component might have two Cl molecules with them. 2Br is something entirely different. Let's work that one out. So this is the example of that fluorobenzene. Now, fluorobenzene is something like this. This is C6H5Cl. So C6H5Cl with 35 is 112. C6H5Cl with 37 is 114. There you go. Now, this one is M peak. This one is M plus 2 peak. This one right in between is M plus 1 peak because of carbon 13. And the small peak over here is M plus 3 peak. It's when you have Cl37 and carbon 13 at the same time. This one is carbon 13 with Cl35. This one is carbon 12 and Cl35. And this one is carbon 12 with Cl37. I hope all of them work. M plus 1 and M plus 3 are not a part of the course, but I teach them to the students just to be on the safe side, because if they tend to ask a common sense based question, you should know. You should be able to answer it.
Uh-huh.
All right. So probably M plus 1 and M plus 3 are not going to be a part of your paper. There is a very, very sleek chance, a very small chance to that, but I'd like to take my chances. That's why I told you. Okay. So M plus 2, M plus 2, M plus 4, and M for the bromine-bromine ratio. Now the ratio is 1:1 because this is 50% and this is 50%. Okay. Now this would be M plus 2, that would be 1:1, and then 1:1. If you work these one out like this, like we used to do, this would be 1:2:1, because this one in center would be 1 plus 1. Hence the peak height would be this. So in case of two bromine molecules, it literally works like this. This should be a little bit long. So 1:2:1. The
Two
peak heights
ratio
are
one.
literally like this, which is M plus 2, and M plus 4, right?
All right.
Again, M plus 4 are not included in the syllabus. It's an extension content. So the chances are there would be no questions related to M plus 4. However, I have taken the questions out of Save My Exams and Save My Exams, and they actually taken questions out of the previous A2 papers, paper 4, the A2 theory paper, and those questions give students a chance to practice all of this extension content. So there would be nothing in the paper based on extension content or on common sense question that you wouldn't be able to answer. All right.
All right, sir. Yeah, you sent me the zip file. I think I have it
Good.
for the
And
analytical
I
chemistry.
also have those converted into a video. So I can share the video links with you if you want to discuss them with
Yeah,
me or
that would be
practice
helpful.
them with me, or if you want me to send me you the video, it's entirely up to you, whatever you like.
You can send